Okay, hi everyone. I'm recording lectures on FPGA architecture, and later on I'm going to record the FPGA CAD algorithms. And for the FPGA architecture, I had some older slides that I could use, and this is the first set of the slides that I'm going to use, and that basically covers the basics of FPGAs. And then after this, I'm going to use another set of slides from Xilinx that talks about some of the more modern and recent features of the FPGA. And also, I'm going to use another set of slides from Peter Chung in the UK to cover basically. But I mean, this set of a slide would be the major one that I'm going to spend time. The rest, I'm just going to point to some of the information that are useful in those slides, and I'll just let you know, um, and I'll let you know how, what part of the data to read. Okay, so before I talk about FPGAs, basically I need to talk about the general method in which you design chips, not just FPGAs, but for custom designs or ASIC designs. And basically what you do is you start with some specifications. Those specifications could be stated in plain English, they could be sketches of what you want to do in the design, and then you go into high level description. And in the high level description, basically you translate it into things like HDL, behavioral HDL, system C, and stuff like that. And after you do that, you go to structural description. And in the structural description, then you are describing things in more detail. So here, you just say, I need to add A plus B, put the result in C. Right? Here, in the structural description, you start talking about how many bits am I going to use? Is it signed? Is it unsigned? What kind of multiplier? Am I going to use a Booth multiplier? Hello? And basically, questions of that sort. So basically, you're going into more levels of detail. And then from the structural description, you go to logic description. So the logic description now doesn't just say that use an adder, but it also says use an XOR gate to add, AI, BI, and the incoming carry to generate, a sum at bit position I, and also, take the majority gate and find the carry out of the signal. This step is usually called synthesis, and it's done automatically. I mean, it wouldn't be reasonable to expect people to do this step. And from the logic description, which could be generic, so you could specify your system as the AND of 10 inputs, right? And that doesn't care if you have a 10 input AND gate in your library or not. It's just a way of describing things. And once you want to go to more specific design that targets the specific library that you have, you do this step that is called technology mapping. And this is one of the biggest differences between FPGA and ASIC design, and I'll talk about that later. So basically, in ASIC design, if you have a 10 input and description in the logic description, then you have to break it up into a tree of 2 input or 3 input AND gates and NAND gates and so on to have the same functionality, but something that maps to the actual gates that you have in your system. And then after you have that, then you have physical design. We spent the whole 5301 talking about placement and routing and stuff like that. And once you have that, you have the fabrication, and then you have the packaging. And obviously, I mean, this is a cartoonish, very simplified version of how things happen. I mean, I did talk about verification, which needs to be basically backtrack everything that you have in, say, logic description and connect it to whatever you have in a structural description to make sure that you're talking about the same design. I'm not talking about, things like testing. I'm not talking about design rule checking before fabrication. And obviously, this will not be a linear flow from specification to packaging. You have to go back and forth as you find bugs and some of the system specifications change, so you have to adapt to those changes. So in terms of the target platforms, and this list that I've listed on this slide could go on and on. I mean, I haven't included things like PLAs and some of the stuff, ROMs for implementing things that you might have covered in your logic design. A lot of those technologies are obsolete by now, but basically you have these four major categories of platforms that you can implement things on. One would be the full custom, and for that you spent 5323 and 5324 doing these layouts and basically drawing these transistors and polysilicons and diffusion regions and so on. And that's the one that gives you the best performance. All right, so you have designers with lots of experience, and they can optimize the system a lot. But that takes a lot of manpower. So an easier way of implementing, and that's what the majority of companies are doing, would be standard cell design, in which you manually design, or some other company designs AND gates, NAND gates, XOR gates, adders, and stuff like that. And what you do is you then map your design into these standard cells. And basically, the main advantage of the standard cells is that you can automate the process of floor planning, routing, placement, and so on. And again, you must be familiar with this, with what we did in 5301. Now, if you don't want to go through the fabrication process, you can choose FPGAs, field programmable gate arrays, and I'll spend a lot of time describing the architectures and so on. So basically what happens here is that in the ASIC design, let's say you have 10,000 chips that you want to send to the market. Let's say you're a very small company and the volume is 10,000. But the mask costs and the design costs and so on, all of that is going to be pretty expensive. So if you pay $1 million for the mask set, then that $1 million will be divided between 10,000 chips, and that would be expensive, right? But with FPGAs, you rely on big companies like Xilinx and Altera, and those are going to make 10 million or million chips of a particular family, and that means that the mask costs and some of the fabrication costs would be amortized between the high volume. And what you do is as a small company, you can only buy 10,000 chips here and implement your design. Another company could take 20,000 designs and so on and so forth. So all of these companies are basically using the amortized fabrication and mask set costs of the FPGA, and basically have a cheaper set of designs. And of course, nothing comes for free. So when you move to field programmable gate arrays, you have to pay a lot of penalties in terms of area, in terms of performance, in terms of power, and that I'll talk about later. But the good news is, potentially you could have your design out in a week or so, right? You don't have to wait for any of the fabrication stuff. You can do in hardware testing, and that's going to be very useful. Now, traditionally FPGAs have been used for rapid prototyping. So if you're Intel and you want to simulate your next generation processor, you can basically buy a rack of FPGA boards. Each of these boards might have 4 FPGAs on it, and you could basically map your next Intel processor on, let's say, 10, 20, 50 FPGAs, and instead of simulating things in software, which would take forever, you can simulate them on in hardware, which is, even though much slower than the target Intel chip, but orders of magnitude faster than software. So that had been traditionally the main market for FPGAs. But as FPGAs got better and better, and the performance approached that of standard cells, then people used FPGAs in the actual final product that people ship. So Cisco, for example, uses a lot of FPGAs in their routers, and that's because FPGAs can now deliver the performance that you need. And of course, I mean, you have microcontrollers and you have microprocessors. These run based on instruction sets, and in that regard, they're programmable. But in terms of performance, they're not necessarily as good as FPGAs. If in your design you need 10 multiplications, you can instantiate 10 multipliers on your FPGA and run all of them in parallel. But if in your microcontroller you only have one or two multipliers, then you basically have to serialize these operations and basically map to whatever features the microcontroller has. Now, in custom design, I can pretty much just skip this. I mean, you guys have seen it probably in your VLSI design, but it takes a long, long time. And whatever you draw in terms of where your P transistors and N transistors are going to be, that's going to be fixed. And the way that you quote unquote program this thing is by drawing where the transistors are and where different materials like polysilicon and diffusions meet, and essentially doesn't have much flexibility. If you have a bug, you have to go back and redraw things, and the whole process is very costly. Standard cell, you limit yourself into fixed heights, and you limit yourself in terms of, where the power and ground lines have to go through. So these limitations obviously mean that you won't get as much performance improvement as you could have done with full custom, but then standardization means that, CAD would be much easier to deal with. Um, Now, in terms of FPGAs, I threw out this word programmable, but where does the programmability come from? FPGAs have three basic modes of programming, and once I show you the architecture, it becomes more clear, how you would program the FPGA. But basically, you have three ways of programming. The most common one is SRAM. So you basically write zeros and ones into memory blocks that control the behavior of the chip, and that's the common mode of programming. And the good thing about it is you can reprogram it. So let's say you do a design on a particular FPGA, and the zeros and ones that you put into this SRAMs tells what functionality you have. You have multipliers, you have adders, and so on. And you figure out that there was a mistake, there's a bug in part of the hardware. So basically what you need to do is you basically need to change these ones and zeros in the SRAMs, and you could use the same chip to basically reprogram the chip to do something else. You also have EEPROM and Flash, which is gaining more and more popularity with FPGAs. It's just that once you lose the power to the chip, you still are going to keep the configuration, which is not the case in the SRAM. And also, and the major players in the SRAM and increasingly Flash are two companies, Xilinx and Altera. There are other smaller companies too, but these are the main two players. And then you have Actel, which makes anti-fuse programmability. So anti-fuse programmability basically uses some fuses or anti-fuses where you apply high currents or high voltages on something, and then you permanently make a connection or disconnect a connection. And basically using this method you can program the chip. The good thing about it is it's much faster compared to SRAM because you're not using things like pass transistors and stuff like that. But the bad thing is you can't reprogram. So once you burn the chip, that's it. If you find a bug, then throw it out. You have to use another chip. And in terms of the layout, this is a simplified cartoon of what FPGAs look like, and the most prevalent architecture is the two-dimensional island-based FPGAs. And essentially, what this is you have an array of functional units. So these would be implementing things like AND gates, XOR gates, adders, and stuff like that. And you have an array of switches. Think of these as intersections in streets in a city, and then you have tracks that actually carry the signals themselves. And I'll talk in more detail about how these are designed and what different options you have. But that's essentially it. This is what an FPGA is. And if you look at the basic structure of FPGAs in the past 20, 30 years, this has been the backbone of FPGAs, but over the years, people have added more bells and whistles. They've added more specialized features like fast carry paths for efficient implementation of adders. They've added multipliers, RAM units, and stuff like that. But this is essentially the basic principle of all the FPGAs. And these are the Xilinx and Altera versions. And of course, I mean, here I'm showing you a flat hierarchy, but it could be hierarchical as well. But again, I'll talk about those later. And in Actel chips, they basically adopted something similar to the ASIC, but since they're not that popular, I'm not going to talk about that part. And remember all of these steps in the design. You still have those with FPGAs. Of course, you wouldn't have fabrication and packaging. These are done beforehand. But you still need to do synthesis. You still need to do technology mapping and physical design. And because the architecture is different from what you have in ASIC, these steps, more specifically technology mapping and physical design, would be significantly different from what you had in the ASIC world. Now, how do you program an FPGA? And this slide is crucial, and I'll try to spend enough time on it to try to make sure that you guys understand. So let's say this is what your logic description tells you. So the circuit with the NOR gate and AND gate and so on with inputs A, B, C, D, E, F tells you what the functionality is, and basically you have an output. Here, this is a very simple example. I don't have any sequential logic. I don't have any flip-flops, but it wouldn't be hard for you to imagine that we could add those and implement those on FPGAs as well. So the first thing that you do is you decide on the pin location. So you would say that I have pin locations ABC here, and then D, E, F would be here. So these would be the inputs. These would be the input pins to your excuse me, to your FPGA. And the next step that you have to do is you have to look at your functional units. So these are the functional units. These are the functional units that you have, and I'll talk about what the functional units are later. But essentially, think of them as RAM blocks that you put the Boolean, the truth table of the function into this. So remember, maybe you have done this in your, undergrad logic design courses. If I give you a 3-input function, and I give you a ROM which has 3 address lines and 8 bits in the ROM, you can basically put the Boolean, truth table of that function into these 8 addresses of the ROM and use the 3 inputs as the address lines, and the output would tell you which one of the bits is going to come out. That's essentially what FPGAs do. That's how they implement logic. So basically, if in the ASIC world you have to worry about, do I have a 2-input NOR gate? Do I have a 2-input AND gate? Do I even have an XNOR gate, or should I, build it using small components? Here in FPGAs, you don't care about functionality. You don't care about the Boolean logic. The only thing that you care is how many inputs do I have. So here I could have 2 gates. I could have 10 gates. I don't care, how complex that is. As long as the number of inputs is limited to 3, I can implement it using an FPGA's logic block. So this is called the technology mapping, which is drastically different from what you do in ASIC. And here I have done the mapping to F1, F2, and F3. Now, once I do that, then I have to decide the locations of these F1, F2, F3 to minimize the wire length from A, B, C, D, E, F to these functions to the output. And something similar to what you did in ASIC would happen here, but again, it has its own specialized algorithms, and you have to worry about the discrete structure of the routing and so on. But I'll talk about them in a later recorded lecture when I talk about FPGA CAD. So once you decide on the placement, then you have to worry about the routing, and the routing could be done using the Dijkstra's method, or similar techniques that we learned in 5301. And here you can see that basically these circles that I'm showing here, the circles are telling me that these are programmable switches, and I'll talk a little bit in more detail about these in couple of slides later, but let me erase the routes. So basically what you need to do is you need to go into this intersection and say, yes, this line has to connect to this line, and then here I have to make a connection so that this wire segment is going to connect to this function. By the way, these wire segments would be electrically disconnected. So this would be one wire, this would be another wire. They're not connected. This would be another wire which is not connected to those, and so on. And there are programmable switches that, for example, say this connects to this one, this connects to that one. So you must have some sort of flexibility in these intersections, in these what is called the switch boxes in the FPGA to design. Same thing happens when you talk about the functional unit. So this line is electrically disconnected from these three lines, and you would program a switch to make a connection. This is basically a pass transistor that says this input of the function comes from this wire segment, which in turn could be coming from this pin or somewhere else, right? So when I talk about these when I show you these circles, the circles show that this is a programmable switch that we program to be on, to connect the two wire segments that connect to it. And essentially you can see that this is the way that you can implement the function, and I can provide digital inputs ABC as 1 0 2 ones and zeros, and look at the function F coming out here, and this basically could be any function that I want. This could be an adder, this could be a multiplier, this could be a really complex finite state machine, whatever that I want, right? So and so far I haven't shown you any flip-flops or registers, but you can imagine that inside those F1s, F2s, F3s could be flip-flops that you may or may not bypass, and that way you can implement things like pipelining and sequential logic and stuff like that. Okay, so this is again the basic method by which you program an FPGA on this vanilla version. I'll stop the video now and I'll record the rest of it later because I have to leave, but I'll continue with these slides later. All right, thank you.